I will be starting shortly. Welcome to another episode of Microcontrollers with kingernorth. This is episode 25, using 7 and 14 segment displays with CircuitPython and Arduino. So let us have a look at what we're going to be doing today. Alright, these are some of the components we're going to be using and a few extras. So on today's show, we have right here, we have an Arduino Uno with running a 2-digit display. And it is just running a sample program that I have on there right now so that you can see what's happening. It's just simply counting up from 0, and it's counting up to 9.9, and then it goes back to 0 and counts again. Secondly, I'll be working with this one over here, which is the Feather M4 Express, which is running with CircuitPython. And this is using a 14-segment display. This one's a 7-segment display with the Arduino. So we're going to be doing the two different ones separately, just to keep it nice and simple. So once we get to that point, what we're going to be doing is we're going to be looking at that code. But what I wanted to show you is that these numeric displays come in different types of sizes. Here's a very small one down here in the bottom right-hand corner. This is one you're probably used to seeing in the size that may have been in your VCR years ago, or on your DVD player. And if you haven't learned how to set the clock, this would be flashing 12 o'clock. It'd be 12:00, and it would stay that way until you finally set the time. A lot of people seem to have trouble with that one, but that is one right there. Here's another one of these displays. These are actually the same types of digits on both of these displays, but they're mounted differently. This one's mounted with what we call a feather format, and it plugs into a base. So I'll show you that a little bit more when I get to the CircuitPython side, since that's what it primarily deals with. And then there's these very large displays. This is extremely large. You can see this from quite a distance away. You might see this at a place where they're putting up numbers to say who's next. Sometimes they'll even be a lot bigger than this. But this one gives me a much, much bigger display. This is like 1.5 inches in size or so, whereas these other ones are less than 1 inch in size. And there's lots of different styles. And there's also different ways to connect them. On this one here has got connection. It's got a 5-pin connector on the back. And this is actually, that 5-pin connector is actually set up for I2C. We've used I2C communications quite a bit. So it works very, very well. In fact, this one is set up for I2C. It has 4 pins, which is actually all you need. And so are both of these. This one is not, and we're going to talk about that because this is actually how they work, and we're going to spend some time talking about how the Arduino one, the one that's connected to the Arduino, works, because this is how they all work. These other ones just have driver chips behind them. This one does not, and I'm going to show you how it works just so you understand it a little bit better. So let me move some of these other ones out of the way because we're not going to be using these, at least not right away, and I just wanted to show you that there's multiple sizes and multiple types out there. And in fact, we'll even move the CircuitPython one off to the side. And we're going to start with this one right here. So let me go to my normal view. And I'm just going to switch down to this normal view. And in fact, what I might even do is bring my camera down a little bit because we don't quite need to see everything. And we're just going to bring it down to here. Now, these displays are LEDs. And this is exactly what's inside of here. This is referred to as a 7-segment display. So let's have a better look at what that really means. So we're going to go look at some photos that I've got here. And we've got this one right here. So this first one I have shows you the pattern of a standard 7-segment display. Now if you count up the number of segments, you have A, B, C, D, E, F, and G, that is 7 segments. But there is another one down here, the decimal point, which is actually an 8th point. But because that's optional, they don't refer to it as part of the 7-segment display. If this is just normal LEDs, which it is, what happens with this is when we look at this, so you have your 7 segments here, and then you have your decimal point down here. What happens is that they get referred to differently as far as wiring goes. So let me just change photos here. And I do have to move over a couple of photos, and it's all the way to here. And the wiring comes in 2 different styles for all of these displays. These displays are either referred to as common anode, which is what this one is, which means we hook up power to all of the segments. So we have segment A, segment B, C, D, E, F, and G, and the decimal point all connected. And then we have the ground pins. And what we do is we actually run all of these pins, these ground pins, to separate pins on the Arduino. Or onto a driver chip if you're using a driver chip to do something like I2C, or you run it through a shift register chip. But generally what happens is we have to connect each one of these to ground while we have power up here, and what happens is that segment then lights up on the display. So if you want to create different segments, so if you want to create different letters, let's go back out to here, and I'll just increase the size of that a little bit. So if you wanted to create the number 9, you would have to light up segments A, B, C, F, and G. You would not light up E, D, or decimal point. You would leave those disconnected. So what would basically happen in that common anode field, where we have power coming in, goes through the LED, goes through these would all be connected to ground. These A, B, C, F, and G would be connected to ground. The others would actually be connected to the +5 by using those pins on the Arduino. Therefore, only these ones would light up, because they're the only ones that would be having a completed circuit. But there's a problem with that. And let's go back to the other drawing just to show what the problem is. So I'm going to skip back over here. What happens is when we bring in this analog connection, each one of these LED segments can draw 5 to 40 milliamps depending on the size of it. That great big display I had, that's a lot of LED you need to light that up. Whereas the very small displays, it would be very small amount of current. The problem is that we have to turn this on through a pin as well. And we're limited to a few milliamps, about 40 milliamps typically on an Uno. Different boards have different current capabilities. So what we do, when we're actually doing this, we wanted to do A, B, C, F, and G are the 5 pins we needed to connect to ground. What we would do in the program is we actually connect all of these to positive, and we connect this to positive. By doing that, there's no current flow because we have 5 volts on both sides of the diode. We add a resistor to the common anode lead, and I'll show you that when I show you how the wiring is connected on the Arduino board. And by putting a resistor in here, we limit the current to what one LED draws. And then what we do is very quickly we pulse the A, we bring it to ground, and then put it back to power. We take B, run it to ground, put it back to power. Take C, run it to ground, hook it back to power. Do the same thing with F and G, and we do it at an extremely fast rate. By doing that, the LEDs look like they're all lit at the same time. And that's how we trick you into seeing the different segments, the 5 segments all lit at once, rather than only one segment lighting up at a time. And I'll give you a little hint. We can actually see a little bit of that on the board that we're using. The other type that's out there, this is the one type. This is the way a single segment is connected when we're using a common anode. There's also what they refer to as common cathode. And the difference is this, instead of being positive, is negative. And then we apply power to each one of these in order to light them up. So it just does it in the opposite direction. All of these LEDs are turned the other way. So in other words, this side down here would be all connected to power. And then this side you would ground whichever one you want when you want to trigger it. And that's basically the same idea. It's just done in the opposite direction. So you have to know whether or not it's a common analog or a common cathode, common anode or common cathode when you're first working with these boards. So there's a little bit of a trick, and I'm going to show you that very quickly on this other board, how to determine which one you have. Okay, it's actually not that hard to do. So that's what's going on there. So let's look at the wiring that we're going to use on this Arduino, and then I'll show you how to test it. I'm going to give you a little test before we get into the programming. So when we get to the Arduino, this is what we have wired up here. This is exactly what I have wired up on our demo today. So here I'm using 2 digits. Well, the nice thing about using these types of digits is that those 7 segments plus the decimal point are the same on each one. So those are A, B, C, D, E, F, G, and decimal point DP. They're just all connected together. In fact, you can see this little gray jumper here jumpers over to this pin, which is the same pin location as it is on this chip, and so on and so forth. In fact, let's follow the yellow wire, because the yellow wire is connected to pin 6, which happens to be the A segment. So it comes up to here, it makes contact here at this point, and then jumpers over to the same spot, A, on the other one. What changes is this pin that's on the end here. So what we have here is we actually have a pin here, and this is for pin 1. This is all on one chip. So what happens is, this is telling me it's the left-hand segment. This pin way down in this corner is the right-hand segment. So this comes across, and each one of these is connected to a resistor, and they have their own independent connections made on the Uno. So when I want to light up the number 0, which would just be on this upper segment, because the decimals are at the bottom, I would have to light up A, B, C, D, E, and F. So what I do is I take all of these pins and I ground A, B, C, D, E, and F. And then what I do is I apply power to the right-hand segment to pin 5. And that only to pin 5, and that would give it to me. And what I do is I pulse these other ones really fast so that I light them up in a circle, and it looks like the number 0 to you. Because I'm going to light these at extremely fast rates. Something our eye can't tell the difference at. And then if I need to put something on the left-hand display, then I power up this pin on pin 4 is my left digit, and I pulse whichever A, B, C, D, E, F, G, and the decimal point that I need to get the display that I want. So that's basically how it works. So that gets a little tricky, but luckily there's helper files to help us with this. So let's just have a look at the board. So I'm going to go back over here, and I'm going to turn off this image here. This is our board. We're going to go back to the camera zoom so I can show you how to test this. So on the back of this chip here, there's actually 10 pins. Those jumpers that go from one segment to the other, they're already connected on the back of the board because this is a single piece. What happens here is when you're going to do this is you would normally have power, and this is our right-hand segment, so the 3, then the 4, then the 5. Every time you see that, it goes through here. If you look very carefully at this, you'll see what I was talking about, how they do it in pulses. There's a very slight pulse that the camera is able to pick up. If I shadow that, you can actually see it maybe a little better. You can see that little pulsing going on with the numbers. It's just slightly there. It's not huge, but it's there. So it gets tricky. And let's see here. There it is with the shadow. And there's a slight pulse there. It's happening at such a high frequency that we barely notice it. Under normal lighting, in fact, if I look at the board itself, I can't tell that it's flickering. But I can only tell because of the camera. The other thing we can do is when we go to test one of these, we just unplug this chip. And I can unplug this chip. It's not going to hurt anything while I'm doing this. And we can see on the back, we have 10 leads on there. There's 10 leads on that chip. And all I do is, using the resistor, I connect one side to power, and I connect the other, and I connect the lead off of it to use as a jumper, like this red one. And then I hook one to ground, and then very carefully I go from one pin to another, and I see what lights up until I figure out which one's the common and for which segment. And then I can light up and figure out which one's A, which one's B, which one's C, and I can work my way around just attaching it to those different pins until I get happy and see where it actually works. And once I've done that, this thing is ready to go, and all I do is I create myself a little slip of paper. In fact, when I did this is the little piece of paper I created. I drew out the chip, I drew out my segments, and this was a common anode as I found out. And what I did was I did DL for digit left, DR for digit right, and then I marked the rest of them for what letter of the segment they lit up. And by doing that, I had my map. And that's what I did. I created a map of how that chip works. So let me plug that chip back in. Let's see if I get it back in the right spot. It should just start working. And there it is. It's still running. So it just plugs in. It didn't bother the program at all, the fact that I had it undone for a moment there, for a minute. So that's what we do to test them. We do that and we actually get it going. Now, I have a simple program running on here that we're not building today. This one, it just goes through, and this is a sample program. Was set up for a 4-digit display. I modified it for a 2-digit display because these are available as singles, doubles, triples, and quads typically. So you can get them anywhere from a single digit to up to 4 digits typically on a single display. So this one here, this was testing, and this was my way of testing this one nice and easy. And by doing that, I can see where I need to light up and when. And I also have the decimal point in there as well lit up. So I'm just counting the numbers, and I just wanted to leave a decimal point on, so I put it in there, and this is actually how many seconds goes by. So it's 100 seconds for it to get from 00 to 99. So that's what it's doing. It's just counting. It's a very simple count. What we're going to be doing is building a car counter. So a car counter is going to be working. Good morning, Brian. Don't worry about being late. You just missed some of the description on how these things work. So, and I showed you a couple of different samples earlier. But we're going to get into programming this one now. But we're going to create the car count program as opposed to this simple counter program that I have running here right now. In fact, actually, the car counter is simpler. So let me come back out to here, and we're going to get to our standard Arduino sketch here. First thing I'm going to do is I'm going to save this, just like I do every other week. So I'm going to go File, Save As. And when I save this, I'm going to take it and I'm going to put it into my show notes. Yes, we are all the way down here to Segment Displays, Episode 25. This list is growing. I have all these pictures here. I have folders with files in them. So let me just create a new sketch. So this is my live car count. So that's what I'm going to call it. I'm going to hit enter, and now let's put that name up here, live car count. Now, one of the things that we need to do whenever we go to run one of these chips is we want to be able to hook this up, and we want to be able to use a driver for it. Because of the timing that I was talking about and the fact that you can see this flickering, I need to be able to set one of my display pins either for the left or the right hand digit, and then I need to pulse only one of the different segment pins. So in order to do that, it's easier. I could actually write a program to do that. And in fact, if you wanted to connect a resistor to every one of these other pins and then use a digit pin, theoretically you could control it. The problem is the current would be too high. So if I had to do the number 8, for instance, all 7 segments of the display would be lit. That's 7 times even 10 milliamps. That's 70 milliamps. That's too much for a pin on the power pin. So you'd have to use a transistor or something else. So we're better off to use the helper file. So I'm going to show you where that helper file is because it doesn't install in the standard Arduino program. So I'm going to go under here under Sketch, and I'm going to go to here, Include Library, and I'm going to look up Manage Libraries. Now I've already installed it, but I want to show you where it is. So I'm going to go into here, and I'm going to go Manage Libraries, and it's pulling up this here. And I'm going to type it in here, and I did some research on the web to find out a nice simple one. And in fact, the nice simple one is called SevSeg for 7 segment. So if I do that and I search, there's one called SevSeg. There's also Seg Shift, which uses if you read the descriptions here, this one uses a shift register to support it. Whereas this one is just the standard one that we're going to use. And I've already installed this. This is version 3.4.0. This is written by Dan Reading or Redding, depending on how he says his name, probably Redding. And it's 3.4.1. I've already, or 3.4.0, which is installed. And if you click down here under the versions, there are a couple of previous versions, but we're using the most recent. We're using the most recent, and I've already installed it. So I've taken care of that for us. But that's where you're going to find it. Just go into your library manager, type in sevseg, and you can pull this up. And when you do, there's more information on here as well. In fact, if I click on that, what's it going to do? It's going to open up a web browser. So that'll let you know, and it'll get you to the full listing of the page, and it will do it nicely for you. The other advantage of this, if you're doing this type of thing, let's see if we can pull this up for you for a moment. I'm going to see if I can, if I open this and I turn on Explorer, let me turn off a couple of this other window here. This is Explorer. So under here in Documents, where is it here? This one. In Documents, I go down here to Arduino. I go to my libraries. You can see I have a lot of libraries installed, but there's sevseg. So if I go into that, you'll see all of this stuff that was on that other page under the help has already been installed. That's part of what the library installs. It doesn't just install one program, it installs all the pieces. There's a keyword text, there's examples, so you'll be able to have example files to work with, the licensing, and then of course CPP and H are the two important files that you add to yours when you run these programs. So that's what goes on there. So I'm just going to close that because we don't need that open, and I'm going to go back to my program, and we're going to work with this. So what I'm going to do is I'm making my life a little bit easier today. I'm going to copy a little bit because I created some of my own text that I want up top, and I'll explain why I'm doing it, because I'm going to be doing a lot of copying and pasting today just because it can get extensive. So I just want to make this a little bit easier, and I want to make you aware of what I'm doing. So I'm going to go through here, and what I've done is I've created my comment section at the top, and this is a fair bit larger than the normal one I do. And this is the reason why. I still have my title and I have my author at the top, as I always do. I put in here a note reference here, sevseg by Dean Redding. I wanted to give him credit in here just because he's the guy who created this great little sketch, or this great little helper file. And it says here, this sketch is used to demonstrate a car counter and display the results on a 2-digit 7-segment display. And then what I did is I created a little picture to remind me of which elements are what on the display. So here's the figure 8 that I've created, and segment A, B, C, D, E, F, G, and this little dot down here is decimal point. This sample uses a common anode display. So I've actually written all these notes in here to remind me what I wanted to use in here. So the next thing I want to do in here is I want to do an include. So this would be my normal include that we always do. So include, let's see, the required helper files. And in this case, our helper file to include this time is going to be, I can just go include. All right, and I'm going to just here, and this is the seg dot h. And of course, I could have just put my cursor there at the beginning and then gone up here to sketch, include libraries. It's actually so far down the list here, it actually scrolls below the page. Oh no, there it is there. It's called sevseg. I could have put that in there and it would have written that same text right there where I just wrote it. So it would have put that in there, and you just drag it to where you want. So that's our helper file that we're going to be using for today. So that's normal. Then the next thing we're going to need to do is we're going to need to create the object, the display object. Quite often, after we've included the helper files, we create the different objects that we're going to use. Today's no different. We're going to do that. So I'm just going to come down here. I'm going to go and create the display object name tag. So this is sevseg, so that's highlighted in a different color because that's my H file. And we're just going to call it sevseg with the lowercase letters. That's what he uses in his, and it's fine, but you could have your own in there. You could call it display 1 if you had multiples of these displays. So you could actually have more than one display running at a time. And then what we need to do is we're going to, one of our standard things we do next when I'm doing this, and I'm going to go ahead and type in the header here, and it's going to be create any pins and variables. Now you would think by the number of wires connected that I'm going to have a lot of pins and items to declare here, but I don't, because that's going to be done in the setup, because that's the way they do it, and I'm going to go through the setup in quite a bit of detail. In here, I do want to include my little push button pin I put down here. There's one hiding under the wires here. There's a push button down here, and this push button is going to represent, in fact, you know what? Let's move these wires down here so you can see it better. I'll just move my push button down. There you go. There's my push button, and this isn't being used right now, so it's not going to hurt the program that's running. It will be involved in our program. For doing a car counter, we want to have something trigger the input to tell us each time a car goes by. Now, I could stand here and push a button every time the car goes by, but we've talked about this in a lot of other shows. We've done things like infrareds. We've done LDRs, which are light-dependent resistors. We've done a few different things. You could use reed switches if you wanted to mount magnets on the bottom of your cars, all that kind of stuff. So you just need something to trigger it every time a car comes by to give me a signal coming in. And that's what's going to be used for our car counter. For today, I'm just using a push button because it's easy. And I don't have to have a piece of track here, and I don't have to have cars running by, and I don't have to have an infrared source and detector all connected. But it still only uses a single input on the board. So at some point, we're going to have to create that. So that's going to be an integer, and it's going to be called push button pin for my case today. And I'm going to connect that to wire to pin location number 2, and that's where it's wired to here on the board. Okay, so that's just showing that that's there. Now we are going to have to create some other variables in here, and I'm going to leave that blank for now so that we can go to the setup file. The setup file is a little bigger than what we're used to. So what I'm going to do is I'm going to copy, and you're going to be happy I'm going to paste this because you don't want to watch me type this all. What I'm going to do is I'm going to take this area here, and I'm going to highlight all of that, and I'm going to go paste. And I told you I've actually put a lot of detail into this to make it easier for you to understand. The original didn't have all this detail in. I'm putting it in so that I can remember how it's done for later, because it's not very often I use this style of board. I normally use one that's already connected to I2C, which does a lot of this for you in the background. So it says set up the variables for the display, and it says here number of digits in the display. So in my case, there's only 2. When I looked at the default example file for this, it was set up for a 4-digit display, so I had to change it back down to 2. And then it said pins for used each digit left to right. It didn't explain, it just said here's your 4 pins, but it didn't explain which one was which. So I've added this little note in here to tell me that I'm going to count from left to right. So I'm going to use pin 4 for my left-hand digit, pin 5 to trigger my right-hand digit. So I've done that myself, and I've made myself a note so that I can keep that straight. Pins used for each segment, and the order of the segments are A, B, C, D, E, F, G, and decimal point. And when I look at it here, it just says segment pins. Okay, it's all in bytes because it's nice and small. That's what they want. And this is pin 6, 7, 8, 9, 10, 11, 12, 13. So they're in order. You can change this any way you want. You could change these numbers. I did it down here in order. What happens is I end up with wires crossing each other. They're not in nice even rows. You could change it so that wherever your pinouts happen to be, they line up. But this was a nice simple way of keeping it straight. So it's up to you what you want to do. The next one in here is I have resistor positions, because I mentioned that you can have resistors either on each individual segment or just on the digit pin. And the digit pin is the preferred method for all of these. So resistor position, false equals on the digit pins. True, it's on the segment pins. So by putting it on the digit pins with a 2-digit display, I need 2 resistors. And these are 1,000 ohm resistors I used just to keep it from being full brightness. And the other advantage of that is if I do it the other way and I do it on segments, I need 8 resistors to do it with the segments. So I only use 2 this way. A lot less resistors. Then it says display type, common anode or common cathode. Well, this is common anode, is what we're using here. If you had a common cathode, you would put common cathode in here in place of common anode. And then it knows whether the pins need to be powered or grounded to get each part of it to light up. That's part of your helper file. You just have to tell it what you're using. Next here, update timing. False is used most of the time. And it's just here, update with delays. Yeah, use it, set it to false. Let it do all the timing stuff that it wants. It looks after it. When you look at the display through here, through the camera, you can see a slight flicker. But I can look directly at it with my eye. I don't see that flicker. It's the camera timing of the shutter that actually shows me that flicker. But to see it with your naked eye, it looks just fine. Looks great. Next is leading zeros for numbers. So when I have my numbers counting, if I don't want to put zeros in front of the numbers, so on a 4-digit display, if I want to display the number 1, do I want it to say 0001 or do I want it just to say 1 in the right-hand position? Well, leading zeros, yes, true is equal to yes, false is equal to no. I chose false. I don't want leading zeros, and we're going to use that in our program. I don't want leading zeros for my car counter. If I only have 3 cars, I want it to say 3, not 03. And then the decimal point. It says here, decimal point, false means use it, use the decimal point. True means not used or not connected. So if it's not connected and it's not used, you can put it down as true. And when I get to the car counter, I'm not using decimal points. I don't have half a car, or a third of a car, or a tenth of a car. I either have a car or no car. So I'm only using whole numbers. So I'm going to set this to true to turn off the decimal point because I don't need it for the car counter. And then finally, before I created the name and the tag for this called sevseg, now I'm actually creating the true object here. So this is where I bring in my hardware configuration, which came from this. I bring in my number of digits, which is from up top, which said 2. Digit pins is the way I'm using my resistors. Segment pins, how they're connected, resistors on segments, whether it's true or false, updates, all these different variables have all been set to true, false, and everything else according to these settings in here. And then lastly, what I do is I set my brightness, and I can set it from 0 to 100, 0 being off, 100 being full brightness. Now, I have this turned up a little bit because of the camera and my extra lighting so that you can see those numbers easier. In fact, if I shadow it, you can even see them a little bit better. In a room, what you might find, sometimes you have a dim control on a display. Well, this is your dimmer. You can set it to different brightnesses to make it what you want. Right now, I'm at 90% of the brightness. So that's everything that's in the setup that we can see for now, except for one item, which we're going to add now, and that's the push button. Remember I said we did a push button? Well, we better add the push button. And the push button's pretty simple. So we're going to create that object. We're going to copy here. I'm going to come down here and I'll paste that in. And it says create the push button. The push button in my case, to make life simple to connect, is just pin mode. PB button was the variable I created up top. And it's an input pull-up. And then we did input pull-ups before. That's this here. All I'm doing is when I press the button, it's going to ground. There's power on this coming from the board all the time. And there's an internal resistor for that pull-up resistor. It's internal to the Arduino Uno. So this just makes it simple to connect. So when I press it, I actually get a ground or 0 volts. When I'm not pressing it, I get 5 volts on the input pin. Simple as that. That's what we're doing. That's what we're looking at. So that's what all of that's about. We'll add the other stuff later. When we go to create our loop, there's a few things we want to do when we're doing our car count. And the trick is when you're writing any of these sketches is to come up with what is it you really want to do. Well, when I'm going to do my card counter, basically what I want to have is I want to have every time the push button, in this case, is pressed, I want it to count one car. But in order to do that, I need to be able to count the car, I need to be able to count the number of cars, and then I need to know when to reset it. So one of the things I use is I use a timer to tell me when it's no longer active. So when this hasn't been pressed for a while, I must be finished seeing my cars. I want the counter to go back to 0 so I can count the next train that comes through without having to press a button. I don't want to have to reset it manually. And these counters can become very handy. You might use this counter when you're entering or exiting a yard to make sure you have all of the cars you're supposed to have. If you're supposed to have 15 cars, you could count this. It'll probably count the locomotive as well. So when you go through, it might say 16. Well, I got the 15 cars plus one locomotive. Maybe you got one caboose, so it's actually going to be 17. Then you'll be able to know I have all my cars that I'm supposed to have. The other place that these are very handy at is on a model railroad, is when you're going through a lot of hidden trackage. Hidden trackage is very commonly used when moving from one level of your model railroad to another in the form of a helix. So what you want to do is you want to count your cars as they go into the helix, and then you want to have another counter that counts them as they come out of the helix. And by doing that, you can say, hey, it said I had 17 going in and I have 17 going out, therefore I didn't lose any cars inside the helix in that hidden section. So that's a really handy feature for you. You could also use that if you're going into a hidden staging yard where you can't see the train. You want to make sure that all the cars made it through all your switches on the way through. Well, I had a 7-car train. I'm pulling it onto track 3. So what you do is you count it, and if it comes up and it says there's 7 cars on track 3, then you know you've done it. So you could have a number of these counters hooked up on each individual track or on the exit track so that you know when you're pulling out, hey, I'm supposed to have a 12-car train. You pull out of your staging yard, it goes through the throat, comes out on one track, and it says, yeah, you got 12 cars, so you're happy. So there's lots of things you can use these for. It doesn't just have to be for counting cars in the visible area, but it can also be used where you can't see it as a reference. So let's go ahead and then let's put all of that together. So one of the things I'm going to need to do is build a timer. We've done these on other programs. This is actually fairly straightforward. We're going to put this into the loop here. So I'm just going to start by get the current runtime from the processor, which is current time equals mils. So it's actually going to grab the running time on your processor, and that's the time since it was powered up. So that's going to be done. The next thing I want to do, if I copy this down here, is I want to check if the push button has been pressed. So I'm going to do a couple of features here when I press the push button. So first of all, I look for PB state. PB state is equal to digital read PB pin. So I'm going to look at that push button pin. I'm going to count it. And what I'm looking for this here is I'm looking to see whether it's true or false. If I'm not touching it, because this is an input pull-up, this will be true. If I press it, it will be false. So in my next part of this, when I'm checking for my push button being pressed, I check if, not push button state. In other words, is the push button state false? And is the car count false? Car count is something that we set in here, so we only read the push button being pressed once. I don't want to have multiple signals coming in. Every time it scans through the program, I don't want it to count another card. I want to count it when I press it, and I only want it to count for one count. So here, very simply, I take my car number and add 1 to it. And then I take my reset time, because I don't know whether this is the last car or the 20th car. So I take my reset time equal to the current time, which I just read, and add, in my case for the example today, I've added 10 seconds. You might want to add 15, 20 seconds if that's your case. Don't forget, time is counted in milliseconds on an Arduino. And then finally, I set car count to true. That saves me on the next scan of this cycle. I don't read the push button still being triggered, because it could take a half a second for that car to get out of the way of the sensor that you've put in there on the layout. And during that half a second, this thing would have scanned many, 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 many times, and you would not want to have it counting each time it's scanned. You wouldn't want to count 422 when it should count 1. So that's what we're doing there. The next thing we have to do is we have to say, well, what do we do when we let go of the push button? How do we reset that car count true? Well, we can do it quite easily. We just come down here, we put in our next little statement. So this is, the first part here is all about when we press the button or we see the input, and this is when we don't see the input anymore. What we do is reset the car count when the push button is released. So if push button, in other words, has it gone back to being true, and car count is also true, because this was set true in here. So when the button's been released and we've counted the count, then set it back to false. That will allow us on the next input to read and increase the counter by 1. So these two can go back and forth, and by doing this, we only get 1 per push. Nice simple way of doing it. Then what we want to do is we want to be able to reset this whenever we get to the point where, let me just go down a couple lines, put this in, because this is kind of a new area that's not related. So it says reset the count total when reset time reached. So this is why we reset a reset time. Every time we see an input, we update our reset time. If nothing has happened for 10 seconds, then we're going to say, hey, is the push button not seeing anything at this point? And not car count. In other words, we went through this state, we reset the car count, so we didn't get stuck with the input on because somebody stopped a car in front of it. And finally, is the current time greater than the reset time? And the reset time was just current time plus 10 seconds last time we saw an input. So when all of those conditions are met, we just take the car number and make it equal to 0. Simple as that. Well, guess what? We've actually done almost everything in this program we need. There's only one last little bit to do. And we're going to come down here now, and what we're going to do is we're going to throw that in here, and we have to update the display that we're looking at. And when we update the display, we're going to take sevseg.setNumber, and we're just going to put that car number. We're going to put in how many times we counted from up here. So as we count, this number is going to be increasing, and then we tell it to refresh the display, and we put this, make sure that it's run repeatedly so that on every scan, that update's going to be, the display is going to be updated. Now, before I save this, I do have one last little bit to do, because I've created some variables in here like current time, reset time, count car, but I never declared them up here where it's any pins and variables. So I have a lot of variables I need to add. So you know what? We're going to add those variables to the program. And a lot of times I go back and do this afterwards, because as I create my program, that's how I build up what my variables are going to be. Until then, I'm not 100% sure. And you can add these one at a time as you do them, or you can just add them as a group when you're finished. And these are all the different ones that we have in here. So the first thing I had was push button state. I wanted to know the state of that push button when I read it. So I put that in, and I default, since I'm using an input pull up, it'll be true almost all the time. I'm going to set it to true to start with. My car counter, I want it to start as false, because I want to be able to tell when the push button's been pressed to go ahead and increase my count by 1. So I'm going to start with it false so that it will count the first car. The number of car numbers. Where do I want that count to start? Well, I probably want to start at 0 because I have no cars at this point. Current time and reset time will be reset by the program as we use it, but we're going to just give it a default value of 0 when we first start, and it'll just get overwritten as the program runs. So all of these variables here, other than the pin, is going to change as this program runs. If I've done all this correctly, I should be able to validate this. There's the big trick. How many times can we do this and not make a typo error? So let's give it a try, and I'm going to verify this. And if I verify it, hopefully it's going to come up with the right answer. And it says compiling sketch, so it hasn't finished thinking yet. First time through always takes longer. And no, it does not. What is missing here? Something I probably typed in. And it says I'm missing a bracket. somewhere, and it's this one right here. Look at this. I have an if statement open up. When I copied it, let's put that in. Oh, wrong bracket. Let's put that one in there. Now that one's there. Let's go down here to the bottom. If I put that one there, where's the bottom of this program? Let's go that way. If I put my cursor there, it tells me now it's at the void loop. That's the start of the program. So we validate. This is why we validate. Even copying and pasting, because I did it in sections. I actually had this program already built. You can see that it's easy to miss something. So we're compiling the sketch. It says it's done compiling, and I didn't get any errors this time at the bottom. So therefore, we're good. Now we can see that we're only using 8% of the program space in here, and only 7% of the bytes for memory for our variables. So we're actually pretty good size here. It's not a very big program. I just wanted to get rid of that other part there. So now let's go ahead and upload this. So I'm going to check my tools. I am connected to COM4, which says that's my Arduino Uno. So now I can turn around and I'm going to go ahead and upload, which is going to compile again, because it likes to do that every time. And then it's going to upload it to the file, and I'll show you how it works on the board. So there it is. It starts with the number 0. And like I said before, there's no leading zeros. So there's no zeros in front of the 0. It's just a 0. And this would be up on your display all the time. As the cars go by, every time I push this button, I get a count. Now I can take a moment to do this so it doesn't have to be real fast. I can also, you get a fair bit of flexibility in here. And that's that reset function. And there it is. It's gone back to 0. Uh-oh. It looks like we dropped a few frames there. Looks like we're heading solid again. Okay, so let me repeat what happened here. I'm not sure when it started dropping frames. We haven't dropped frames for quite a while. This is unusual. I'm not happy about dropping frames. I just turned one other thing off that might help us with that. So this is at 0. Let me go through and do some counts again. So we're going to get it up here to, we're going to go to 16, 17, 18. No, let's go to 21 cars. And what we're going to see here, I press that button 21 times. After 10 seconds, we're going to see that that drops down. So hopefully those frames didn't cause you any problems. Just counted really fast. Yeah, you know what? That was the kid that I gave the controller to, and he ran it and he turned it up to full speed. You know, we get that sometimes, so you know that on your own layout. Your layout, my layout, Walter, tend to move really slow. We did see this reset to 0 while I was busy talking. So this worked. So that means this program worked the way that I wanted it to. So luckily, everything in here seems to be working. We seem to have the program. You can take your time and scroll through this program. So if you wanted to grab some screen captures, we started out with that. This would allow you to pause. I give you a few seconds. You can hit pause on the playback. We go down here. This is the next section of code. Just follow your line numbers to make sure you don't miss anything. All the code is there. Comments might be cut off, but there's no code cut off in this. All right, so you could freeze that image and then continue on. We'll continue down to about there. Just use your line. Actually, I think it was about there I needed to be. So we're going to let you get that. Oh, this one here is a little cut off. So we'll just move over there so you can catch the rest of that line. That one line that's long. I got one long line of code, and I think I got one near the bottom. And I'm going to show you the loop. The loop is broken into a couple of parts here. The main loop here, this is the press my push button, release my push button. Okay, that's it. When that one's working, then the big thing down here is the reset time. And this is the last bit of code here, and this is the end of it. It's only 84, even with all those comments in there. It's still only 84, and if I scroll back to the right here, you can just see the current time and reset time. That was the rest of that line, so that you can make sure all that works properly. But that's it. That's the whole program. So everything's there. It looks like we're holding. I don't know why I was dropping frames there. Something must have been happening in the background. I dropped a few frames. So there's your code. So now what I want to do is I want to move this one out of the way, and I want to show you how we do this in CircuitPython with a 14 segment display on I2C with a little bit of a change to it. Okay, so let's do that. So let me turn off this code first of all, and let me turn on the CircuitPython code. So let me move this board out of our way. And we're going to bring in this board, and while we're at it, we're going to zoom in a bit more because this one doesn't need as much room. And there it is there. There's our other board. So this is an Adafruit. This is from Adafruit. This is the Feather M4 Express. This is a common board we've been using all along. This is a 14 segment display. So this one looks a little bit different. So let's go look at my pictures again to show you what's happening with all of these. So we're going to move over on these pictures. And actually I got to go the other way. There it is there, and increase the size of that. This is the layout of the pattern in a segment. This one has all these extra segments in it. So what happens here again, we still have A, B, C, D, E, F, but G is broken into two segments, so they're actually referred to as G1 and G2. That way the letters match what they were on the 7-segment display. The decimal point is still DP. But now we have all these extra ones here. After G, we have H, I, J, K, L, and M. By having all these extra segments, it allows us to do a couple things with the display. One, it allows us to have fancier looking numbers because we can use slopes. The second thing is we can actually display letters, capitals, uppercase, and lowercase letters on this because we actually have a lot more pieces to play with. And I'm actually going to do that in my program. I'm actually going to use some letters as well as numbers to do a few things on this display. So I wanted to show you that. The other things that's going to happen in here, I have to just zoom this back down, then I can change images. This is our board wiring. Look how few wires we have when we use an I2C board. So this is the same as the one we're using here. This is the Feather M4 Express. I put it on a breadboard. I've got my power, my 3 volts and my ground going here. They are connected to these boards. Now there's 5 pins on this board, even though this backpack is for I2C. 2 of them have power on it. 1 has ground. And then the last 2 connections, there's actually a D beside this pin that's connected to SDA. And the C is connected to SCL. So data and clock. Those are the data and the clock pins of I2C. And of course I have my push button here connected to D4, and it's grounded on the other side. So it's going to be an input pull-up that we're going to use for it, the same as we did in the first example. So this is all the wiring that's required. This would simplify your Arduino wiring considerably if you used an I2C device as well. Your program would change, but it allows me to do it because this board has a chip on the back side that does the communications and sets up all the displays properly to be used. So with that said, let's go look at our program that we're going to be using to make this work. And I just got to get my mouse down here. There we go. So this is my car count program. I hope that's large enough. If not, I can make that a bit larger. In fact, I think we'll go ahead and make that a bit larger anyways. There we go. So we have car count, and this is by me using an Adafruit M4 Express. So what I've got here is I'm using CircuitPython 5.3.1. Very shortly, we're going to be going to version 6 of CircuitPython. So I may start using that very shortly. And so I'll have to update this number. But this is a very growing trend on CircuitPython, and the numbers are growing very quickly. So because of that, in my program, I put in what revision I used so that I know which set of files I'm using with it. And if I update this to 6 later on, I'll update this note and I'll make it all work with 6. So again, I'm going to include my helper files just like I always do in all of these things when we're doing it. And I'm going to import time, board, bus I/O, and digital I/O because those things are built into the Arduino setup when you do it. Here we add them so that we don't use up memory unless we need them. So those are all going to be inserted in there. And then I'm going to import the one for the driver for the actual display that I'm using. And this is an Adafruit, and this is an HT16K33, and I'm going to import segments because this is a segment display. They also make a similar backpack, and it can be different displays. There's different versions. There's a 7. There is the 7 segment displays in these. There are the 14 segments, which this one is. There are also other displays and of other sizes that can be used, and it may or may not use this driver chip. So this is the one that's used for the display I'm currently using. In fact, on the board, when we look at the image, it's really hard to see, but down here at the bottom of the board, where you can't see it, way down here, it actually tells you that it's an HT16X33, or K33, pardon me. That's all written right on the board. I don't know if I can tilt that up. There it is there. And it's typed down there, really small print, but it's there. Okay? So you just have to match it up for the board you're using. And this is going to be the same no matter whose I2C board you're using. If you're using one that's 14 segments and uses that driver, that HT16K33, it doesn't matter what size it is or who makes it, as long as it's I2C and uses that driver. You should be fine. But you may have to look up the one for your particular board. It's just like anything else. The next thing we do is we have to create this I2C protocol. So this is our standard I2C bus I/O board, SCL, SDA. That just tells us to use those 2 pins on the board to talk over as I2C. Then it says create the LED segment object. So this is where I'm going to create the object called display. And I'm going to use segments, because remember I said import segments. And I'm going to tell it's a segment 14. So it's a 14 segment by 4. In other words, it's 4 wide. And it runs on I2C. So this is the defining of the object. Instead of all those big long parameters, this is all I need to put in there. The rest is already set up. The next thing I do is I can clear the display, and I use display fill. So very similar to the idea that we used when we were using NeoPixels. I'm going to tell it to fill, and if I tell it to fill with 0, it's just going to go empty. It's just going blank. Then I'm going to set the brightness of the board, and I was playing around with this. I actually ran it at 0.5 when I was using it myself, but then when I put it under the studio lights here, I actually increased it to 0.9 to make it easier to read. And then it says create the required input from the push button. So here's my normal thing for creating a push button. I create PB1 first of all as a digital input output board, and I tell it what pin it's connected to, D4. The next one, I tell it that the direction, and I want it set as an input. This is where I set up either input or output. And then the last part is I want to tell it that it's a pull-up. So I want to use that internal resistor again, just like I did on the Arduino. And this is how we do it in the CircuitPython. So there's no setup file for this. It's all just done at the top here. All my required variables, again, I have current time, reset time, car number. They're all the same as they were in the Arduino program. Car count, display updated, and reset done. These are all set to false. This changes a little bit different because of the way the program works. That's because it's CircuitPython as opposed to Arduino, so there's a slight variation. And then we get our while true. This is our loop when we're talking Arduino. So again, the first thing I do is I grab the internal time of the MPC, of the actual the microprocessor. So this one here, current time is equal to time dot monotonic, as opposed to just mils. So this is measured in seconds, but it includes decimal points. You got to remember that when you're doing CircuitPython. CircuitPython likes the decimal points. Count cars when push button pressed. Okay, PB1 pressed. So if not, push button value. So we don't have to read it and then compare it. We can do it all in one step in this one, as opposed to 2 steps in the Arduino. So it's if not. So in other words, if false, PB1 value. In other words, when it's pressed, I'm going to get that false signal. Then I increase my count car by 1. I take my reset time at 10 seconds. Now this is where I use 10 instead of 10,000, because I'm measuring in seconds, not milliseconds. My car count is set to true. My display update is set to false in this one. This is something I didn't have to do in this. And I also do my reset done equals false. So there's a couple of things I have to do in here. The next thing I do in here is display the number of cars. So I don't display it at the end. I actually display it earlier on in this program. So if count car, so if that's true, which we just made it true in the previous group when the button was pressed, and the display is not yet updated, which the display is false. Then display fill means clear out the numbers that are there. And then I use display print car number, which is the number from 0 to whatever it's going to be. It depends on how many cars went by. And then I set my update as true, and then I let it sleep for a very short input. So this is like 25 milliseconds is all this is waiting for. I could probably go less. I did 25 milliseconds. Now, I'll explain why we did what we did here with the display. And the other one, we just set the number and told it to refresh the display, and it worked fine. This doesn't work the same when you're dealing with 4 digits. What happens is it wants to scroll them. So if you don't clear before you print the new number, it just pushes. If this was a 1 for when the first car came by, and you pressed it again for 2, the 1 would move to the second digit and the 2 would show up here. So it looks like 12 instead of 2. And then when you press 3, it would say 1, 2, 3. When you press it again, it would say 1, 2, 3, 4. You press it again, it would say 2, 3, 4, 5. Which we don't want all that other numbers there because they don't make sense. We want it, if we've pressed it, if we've only seen 5 cars, I want it to say 5. Simple as that. So we have to clear this display each time. And once we clear it, then we just print the new number in there. But it does it so fast, you don't even notice it. It just does it. And then what we do is reset the car count when PB1 is released. So this is the same as before, this part of the program. So when the value goes back to true, in other words, it's been released, and we've counted the car, then set the car count ready to false, so we're ready for the next push button incident. And then what we're going to do is we're going to reset the time. So in this one here, this is done here. If the push button is released and not count car, in other words, count car is false, and current time is greater than reset time, and the only thing you're missing on there at the end there is the brackets and the colon at the end for the end of the if statement. So let me get back to the beginning of that line. Then what we do is if not reset done. So if we have not done the reset, so that's why we just set the reset way back earlier. So we actually set it to false back here at the very beginning. We reset the display update to false. And right now the reset is set to false, reset done. So if it's not reset done, so if it's false, fill the display with zeros, set the car number equal to 0. Display, so we're just setting it then print. And this is where I print the word done. And you're going to see that. I'm not going to print, I'm just going to say that it's done. I'm going to delay for 2 seconds. Then I'm going to clear the display. And then I'm going to set it to true. So let's see how that works in the program. So I'm going to bring my finger in from the side here, and I'm going to press that button. And it went to 1. Let me shadow that 2 for you. I think I can. 2, 3, 4, 5, 6, 7, 8, 9. There's 10. It's taking up 2 digits now. And you notice this one for the extra displays, it pushes the slashes in the zeros. So we'll keep going. Actually, so there's 2. That's hard to see. Pardon my other finger reaching over. I'm going to reach over the board. 21, 22, 23. I want to show you the number 5. Look at the number 5. Because of the extra segments, we can use the slopes. So they've actually made it real fancy. They've actually managed to make that fancy. And because I didn't press anything for a while, the word done came up. So that was that reset feature, that 10 seconds. So let me just do this real quick, get a couple of digits. I'll shadow this. We'll wait the 10 seconds, and you'll see on the display it comes up with the word done. And there it is, and it says done, D-O-N-E. And just like it is in my program, the O-N-E are lowercase letters. To prove that that's what it did, let's change this to done, all capitals, and I'll save it. This will update, and you can see it comes up with the big word done, and then it goes away. So let's do it again, just so you can see it here. I'm going to go ahead and trigger that numbers. I'm going to wait. I'm going to shadow this so you can see it when it says done. 10 seconds is a long time when you're waiting, trust me. And now it's all in capitals. So we can show uppercase and lowercase every time. So I just wanted to show that we can do both letters and numbers with these 14 segment displays. They're kind of neat. And if you're doing an I2C one anyways, it doesn't matter. So if you're using an I2C one that looks like this, it's just smaller. You can't display the letters on here because it doesn't have all the slashes. But again, there's a chip there. Everything else is here. It's got the 4 connections for the I2C, so you could do that. You could use that one with I2C. What I did want to show you before I went away is this is another board set up here. This is another M4 Express. If you notice, I'm not using a breadboard on this one. This is using the feather form factor. So I'm just going to unplug this and show you all the different pieces. In fact, I might have to zoom out just a little bit here. There we go. I'll bring this into view. What I have here is I have a board that's already pre-wired. All I had to do was solder the headers onto it. When you buy them, you just get the printed circuit board and the headers. And these are in the pattern of the pin on the bottom of this feather format. Feather format is a unique format that's a standard. So that allows me to take it, plug it in on this board, and it allows me to use it instead of a breadboard. This display, these two displays are identical. In fact, they have the exact same modules on them. They both have the same drivers. It's an HT. It works exactly the same. The difference is this one here only has the pins on it, the standard little pins. So it has the I2C. It only has the 5 pins, 2 for power, 1 for common, and then the 2 communication pins. Whereas this one is set up in the feather format. So it uses all the feather setup already. And in fact, on the back side, if you look very carefully, you can see all the small little solder points that they use to solder the display on there. Because of that, this fits in the feather format and fits on this expansion boards. And these expansion boards are available in the feather format in either a 2-pin, a 2-slot, 3-slot, or 4-slot. And there's 2 different versions of 4-slot boards that you can get for these. So you can put a bunch of them in there. You can also put header pins in here, like through pins. And you could stack this display right on top of it if you even wanted to make it smaller on a single level. So that's just an option. And don't forget, you can also get this great big monster of a display here. So if you really need really big numbers and you need to be able to see them because you've got bad eyesight, you can always use a big display. Again, this is I2C. In fact, I think that's the same pattern. I just can't substitute it in place of this one because this is the 14 segment driver. This only uses the 7 segment driver, so I can't quite do it the same way. So I would actually have to change my program slightly, and I could plug this one into it and use it for my car count. But there you go. I think that works really good. I don't know why we dropped a few frames there in the middle, but we did. But I think it happened during that one update on the Arduino program. Other than that, I think we're all together. So let's just have our little recap at the end of the day. We were able to do this with the Arduino. So we were able to do it on different size displays if we really wanted to. This particular one happened to be the feather. Let's kind of tuck this one up in the corner. We'll kind of sit them on top of each other here. We can do this with Arduino. We can do this with CircuitPython. It doesn't matter. We have similar devices in both. You have 7 segment displays, which are great for displaying numbers. We have 14 segment displays, which are great for alphanumeric and symbols like dashes, greater than, less than. All of that stuff will show up. We're still limited by digits. Mind you, we could, in theory, put these multiple boards. We can use more than one of these boards in a program, so we could have multiples of these back to back if you wanted a wider display, more digits. Lots of choices there. You can play around with it, use your imagination, and come up with lots of choices. So this was our car count program, done with both CircuitPython and Arduino, just done a little bit differently for each one. I hope you've enjoyed this show. I hope it's been good. I don't see any last minute questions coming up on my chat in YouTube. I trust if you have any, you'll leave me a note or send me a a message for those that know me, or send me a message through YouTube. So with that, I'm going to shut down the show for today because I think we've come to a logical conclusion for this. So thank you for watching. This has been Microcontrollers with kingernorth, episode 25, using 7 and 14 segment displays with CircuitPython and Arduino. And again, thank you. Don't forget to follow me on Twitter if you want to know when these shows are going on. I put out announcements, and that's at kingernorth if you're looking for my Twitter handle. And for YouTube, of course, if you found this, you probably know where this is. If not, this is where I'm located, is youtube.com/kingernorth. Give me a likes if you liked what you saw today. Give me a follow if you want to follow along and get notifications. Turn those on if you want to know when I'm going to be broadcasting. And along with that, watch my previous episodes and enjoy the topic. This is, like I say, microcontrollers, huge. I use them a lot with my model trains, but they're used for a lot of other things as well. So enjoy, stay safe, and we'll see you in 2 weeks, which will actually put the show on Halloween Day. It'll be in the morning, but it'll be Halloween Day, and I'm going to try and do a couple of Halloween-themed items for that day. I know it's a little short if you want to try to build them on your own, but I'm going to work on that and see what I can come up with in time for next show. Till then, take care, have fun, keep experimenting.